So our topic today is going to be this deadly human carcinogen that's found in many different ingredients, including laundry detergent, emulsifiers, and this lipstick that I was planning on putting on. So being the skeptic I am, I always like to take a look at the ingredients that formulate this nice glossy finish. So I just looked it up on the H&M website, and I always take a look at the ingredients. And this word right here, very interesting. So it turns out that this polyethylene that's found in the lipstick is a known human carcinogen, and you can always identify it through, the prefix PEG or polyethylene glycol or anything of that sort. And it's a very small byproduct of what happens when you're trying to form ethoxylated fatty acids. And then what you do is a very specific process of ethoxylation. Ethoxylation is just the addition of that fatty acid onto a substrate in order to make all of the materials that hold this lipstick together. So at one end, right, you have the polar substances with the OH and the oxygen being present, and that's what gives its really good watery consistency when you're washing your lipstick off, right? But then you also have the good grease component when it comes to putting the lipstick on your lips. That glossy finish is a result of all these really long carbon chains, which you will see eventually. Unfortunately, when you wash it off, you're adding water. That just amplifies the amount of possible carcinogen going down the drain out into the pipe sewage system, which is not a good thing. So the first thing we want to do is take a look at how 1,4-dioxane would form in an acidic environment. Problem is that when you put it with sodium bisulfate, it ends up dimerizes into this compound right here, which is a known human carcinogen, and we don't really want that in our lipstick or cleaning detergent. So the first thing that happens is this oxygen over here, it's got 2 lone pairs on it, and it's going to take and steal this proton from the bisulfate. That will leave this oxygen with a negative formal charge. But now our problem is the oxygen here has a positive formal charge on it, and oxygens are not very comfortable with having a positive formal charge. They want to have 2 lone pairs and 2 bonds. So what ends up happening is the oxygen grabs this pair of electrons and steals it from this carbon. So then we end up getting this really nice alcohol here. Now we have a carbocation right here. Now we have these 2 parts attached to each other. And now that we put it with water, water is a protic solvent. What ends up happening is, for some reason, surprisingly, it does an SN2 backside attack. Now, I didn't think this was possible because what we're dealing with here is a primary aliphatic. Turns out it actually works. We have 2 lone pairs on this oxygen. It's going to do an SN2 backside attack. This oxygen is going to leave. So now we have this lovely structure with 2 alcohols here. But we are in a protic solvent. So one of the 2 alcohols, doesn't really matter which, is going to get protonated to get this H2O+. And even though this structure shows the positive formal charges on hydrogen, it's on the oxygen. In order for the oxygen to get rid of its positive formal charge, it's going to take away, break this sigma bond. But now we have this becoming a carbocation here, CH2+. Now, in terms of the order and the rates of how this reaction goes, that has to deal with more kinetics. So we're not really going to touch on that. But what I will say is, when one of the alcohols falls off, the other alcohol will then act as a nucleophile for this carbocation. One of the electrons here, looks like there's 4. One of the electrons here is going to like that positive carbocation. That's the power of love. This was our once carbocation, now no more, which is great for us. But again, what ends up happening? We have another alcohol getting protonated. Again, protic solvent, love that. So this ends up happening. This ends up getting a proton here. So now we've got this H2O+, and that's been protonated, and it's going to fall off again because it doesn't like having a positive formal charge. And if you're wondering, why does the oxygen grab in the first place if it doesn't like positive formal charge? Because we are literally being ambushed with protons. Like there is no escaping the protons. They're bumping in everywhere. The oxygen's got 2 lone pairs on it. It's gonna grab something eventually. Once this group falls off, so this is going to become a carbocation yet again. And because we have this at the end, the electrons can grab the carbocation and fold in intramolecular reaction into a ring. And of course, there will be an intermediate that looks like this, OH+. But again, protic solvent, the H would get grabbed and we would be okay. So ultimately, this is how 1,4 dioxane is formed. That's in an acidic condition. Now we're going to move to the basic condition. So in a process of synthesizing ethoxylated fatty alcohols and ethoxysulfated alcohols, we create this byproduct, which is a human carcinogen. So we're going to learn how this works in a basic condition. Because when you make fatty alcohols, basically the process is just overloading a normal fatty acid, carboxylic acid, with H2 on a platinum catalyst, palladium catalyst, nickel catalyst, whatever you have. Basically gets rid of all the double bonds, puts an OH on it, you're good to go. And this parentheses here is just to indicate that we've got a lot of C2H4 groups. In this tail, we have a polar head with the OH, and then we have this really non-polar, greasy chain of just C2H4 all the way through until we introduce ethylene oxide. What ends up happening is we have a basic condition here. There's no acidic, so we're not going to have any, we are going to have a ring opening, but it's not going to be like what we saw previously. This OH here is going to do a backside attack on this carbon right here. And then in turn, that will open up the ring here. So then we end up having a negative formal charge on the previous oxygen in the triangular ring. And then we end up having this oxygen here from the previous alcohol with 2 bonds instead of 1, and the H still on there. And just to note, this has a positive formal charge. So if we got a positive formal charge on one oxygen and a negative formal charge on the other, it's just as simple as taking this proton and moving it over there. It's always the oxygen that's going to be grabbing the proton, not the other way around. So then we end up with this really nice structure in section 3. And these parentheses, again, just to note, this is meant to indicate the number of C2H4 greasy groups we've got going on. And this is meant to indicate the number of times that we add a new ethylene oxide on there, because this reaction doesn't happen once. It happens many, many times. You get this really long accumulation of polar presence with the ether and then the alcohol at the end. So now we're going to be introducing, we can do 2 things here. We can do either SO3 or we can do H2SO4 sulfuric acid. So for now, we're going to use H2SO4 because SO3 will pop up in a very short time. This ends up being protonated by the OH on the fatty alcohol. You got 2 lone pairs here. They're going to grab that hydrogen. Then this is going to become H2O+. And then, because it's been protonated, it's going to fall off in order to take its electrons back. So then we end up with this S has just lost a bond, which means that it's going to become S with a positive formal charge. This oxygen just lost a proton, which means that it's now got a negative formal charge again, like we had up here. And again, my mantra with orgo is plus, loves, minus. I should make it clear that those 2 attract each other and form this new bond here. Meanwhile, we've taken care of the H2SO4, but now we've got something different going on, SO3. Now, SO3, it's this kind of crazy. You've got double bonds everywhere, right? But it can do resonance. You can have an oxygen that once had 2 lone pairs end up having 3. When you do that, you put a negative formal charge on the oxygen and a positive formal charge on the sulfur, like you can see here. Then we generate this not quite a full covalent bond, but an attraction between one of the ethyl groups and the positively charged sulfur. The positively charged sulfur, along with its entire compound, is already an electron withdrawing group. So when you have this oxygen and the sulfur and it wants to hog all of the electrons together in this big cloud, you got the same thing going on here with this group. It's an electron withdrawing group, which means that in the process of pulling away the electrons, you're rendering these two carbons as being very partially positive. So this is going to be partially positive here. And then because this is a good leaving group, it's actually just going to fall off, and this carbon is not going to be partially positive, it's going to be fully a carbocation. So now you must be thinking, no, what to do from here? You got two positive charges going on. How can you make this work? This oxygen here ends up taking electrons with it. So now you've got an oxygen that has a negative formal charge on it. But this sigma bond right here has just been completely broken. But this oxygen here is not attached to this group here. It's still attached to this chain of C2H4s along with an ether in the middle. So you end up having this possibility here. So because you have a positive CH2 here and a negative oxygen from where it took those electrons, you're going to end up with this thing. Meanwhile, let's look at the positive thing instead. We've basically just spliced this chain away from everything else. So now we end up having this group, which was our leaving group, and then we have this positively charged CH2. That was where the fatty alcohol once was. So of course, these two together are going to fall in love, and we're going to make this. This is the product we like. Oh my god. It's an ethoxysulfated fatty alcohol, which is exactly what we want when we have our lipstick, when we have our laundry detergent, when we have our other cleaning supplies. Recently, Governor Andrew Cuomo of New York passed this law, S4389B, basically stating that all cosmetics can no longer issue no more than 2 parts per million of this dioxane, and then for any home cleaning products it can be no more than 10 parts per million, and this has to be all done by 2022, which may not sound like a lot, but when you think about the accumulation, it's a big effect. There's a lot of dioxane out in the environment, in the water, in the air, etc. Moral of the story is, it's imperative that we reduce the amount of this ring going out into the environment because it's not biodegradable. Thank you so much for coming to my combination application to life and reaction mechanism. My thanks goes out to both of them, both my lab instructor and my professor, as well as my SI tutor. Really appreciate her. Anyways, enjoy your night and try to minimize the amount of lipstick you put on.